so I'm Alex Kieran. I'm an engineering tech lead at Uber, and I'll be talking about managing Uber's data workflows at scale. For the agenda, we'll first go through an introduction. We'll talk about how we converge on a data workflow system at Uber. We'll cover some basic system architecture. We'll talk about isolation and multi-tenancy. We'll speak about how we re-architected for high availability and scalability. And we'll go through some takeaways. So I work at Uber. Our mission is to ignite opportunity by setting the world in motion. Data is at the heart of Uber. Everything we do relies on data and is improved by intelligent use of data. One example of this is the Uber Eats app. As a consumer, when you open the app, you're presented with an ETA of how long we think it'll take you to get your order delivered. This is calculated just using past delivery data, using machine learning models in order to train them to get the most accurate prediction for your specific order. Another example is the customer obsession team. This team at Uber is tasked with responding to customer support inquiries and questions and tickets. This team's created a system called CODA, which has used NLP techniques along with deep learning models in order to train on past ticketing data and then can suggest the most relevant suggestions in order, for our customer support agents. With this, our customer support agents are now able to respond much more quickly and efficiently and are able to surface the best resolutions to these tickets using this machine learning system. Data at Uber is powered by a couple different types of people. First, there are the machine learning software engineers. These are the engineers that work on all the microservices and make sure that the data ends up where it's supposed to be. Next are the data scientists. Data scientists look through the data and glean intelligent insights out of that data. Machine learning engineers create the features, train the models, and make sure that we can create accurate predictions. We also have city operations people. These are the people at each city which use data at a day-to-day fashion for their business decisions at a local level. And finally, there's business intelligence use cases such as dashboarding. So the question is, how do we manage all this data? Data needs to be ingested, transformed, dispersed, and also used for various workflows such as machine learning and other workflows. So what's needed is a tool for managing data workflows. So some of the features of a data workflow system include the following. So first, scheduling and orchestration. So typically our workflows need to be kicked off at a certain cadence. So it could be hourly, daily, or a cron interval. So this system needs to make sure that it's kicked off in that specific cadence reliably. Also, typically workflows have dependencies between each other. So you might have your workflow actually listen on a Hive partition. Once data reaches that partition, then it'll kick off a Hive query or a Spark task, and then finally run through a machine learning model to train that model. So the system needs to make sure that all these dependencies are kicked off in that correct order and handles all the different dependencies between the tasks. Workflow systems should also help you to connect to external data sources. So at Uber, this would include connecting to systems such as Apache Hive, Presto, Apache Spark, our data warehouse, which is HP Vertica, and other systems as well. And finally, the system should help you manage and monitor workflows. So if anything goes wrong, you can essentially correct the situation and be notified of that. So I'll talk about how we converge on a data workflow system at Uber. When I started at Uber, we had a proliferation of data workflow tools. So data scientists or machine learning engineers were using a variety of tools to create their workflows. And this included Jenkins, Cron. We also had an open source tool called Uzi. We had a couple of in-house tools written in Python, one in Clojure, and we also had an Airflow-based system. So obviously, some of these tools are not even meant for database or for data workflows, including Jenkins and Cron, and they're obviously not ideal for that specific use case. Also, for our customers, this was a paradox of choice. So essentially, each time a customer or a data engineer or data scientist needed to create an additional workflow, they essentially would have to learn about all the different trade-offs for each tool, learn about all the different intricacies, have to choose for a single tool each time. So this is definitely a high overhead for all of our customers. They need to have a high learning curve to learn all the different tools at Uber. Also for our team, this was a huge maintenance burden. So essentially we were supporting all these overlapping tools and having to maintain them together. And this included any bug fixes or feature requests had to be applied across all the different systems. Also anything like infrastructure upgrade or security upgrades, we'd have to actually patch each of the systems in order to do that. So obviously this was a huge maintenance burden for our team and was not really sustainable. Within our team, we also got some knowledge silos. So essentially, we didn't have a single engineer that knew all the different tools. So this meant that whenever a customer or data scientist would ask us for advice about their specific use case, we couldn't necessarily help them out because maybe we didn't know a specific tool that their use case applied to. Also for on-call, it was a little bit difficult as well. So you might get paged in the middle of the night on a weekend and have to support a tool that you're not familiar with. So obviously this was a challenge as well. And some of the tools, for example, we had an Uzi-based tool that not really only one team member knew of. So essentially we'd get paged in the middle of the night and Eric was the only one that really knew that tool. So really, no matter who was on call, we'd have to actually wake up Eric to get help on that specific tool. So obviously this was not sustainable for our team or for Eric, for that matter. So what we decided to do is essentially converge on a single tool at Uber for data workflows. And this would essentially help make sure our team can better support that tool and give customers and data scientists, data engineers a better user experience. And users won't have to choose among all these various tools as well. So the question is, what is the goal in choosing such a tool? So we kind of have to think about what's important to us in choosing the next tool to kind of unify that system. So the first thing we thought was important is it should be easy to author data workflows. As you can see, we have a variety of engineers at Uber that can write code, which can include data scientists, machine learning engineers, ops people, and they actually have a variety of skill sets. So we wanted to ensure that whatever tool we chose was actually approachable to all these different types of engineers. Also, we wanted to make sure that workflows are expressive and can support flexible authoring as well. Another important thing we wanted to support is basically the typical developer flow that you're used to. So as a developer, you're writing configuration as code. You want to get your code reviewed by other teammates. Once you land that code, you want to have a revision control system to see the past changes. So essentially, whatever tool we chose, we wanted to support that developer flow as well. Also, workflows should be easy to visualize. So this means that at any point, you should be able to see all your runs, kind of see which tasks succeeded and failed at an easy glance without having to dig through different pages of the UI. Also, it should be easy to manage workflows, which means that if anything fails, you should be able to restart the tasks and also perform things such as backfills very easily. And finally, the log should be accessible. The first thing users do when anything goes wrong is to look at the logs to try to debug what went wrong. And actually for our team, this was actually a point of frustration with our previous tools. For example, for the Uzi-based tool, might get paged in the middle of the night, and then we have to set up some Chrome proxy, jump through a couple different servers, and then finally the logs would be gone because the retention was too short. So essentially we wanted to avoid this for users and provide them accessible logs in a single click as well. So once we thought about all these different goals, what we decided to do essentially is converge on a single system, and we converged on Piper. So this is actually the Airflow-based system that we had at Uber. And essentially this was already becoming one of the more popular workflow systems. Most of the workflows were getting added to this. And it satisfies all the goals. It has a Python-based DSL that allows users to author workflows using a powerful and expressive DSL. It also has a maintenance UI that you can manage your workflows, see what succeeded, what failed, and be able to perform backfills and other types of information. And logs are accessible as well. So here's an example of kind of the DSL. And if you're familiar with Airflow, you'd be familiar with this. Essentially, it lets you define a pipeline with a certain IP key and a scheduling interval as well, where you can kind of say if you want to run daily, hourly, or cron. We've also added some data center specific options. You can actually tell it which data center you want to run in as well. And then the middle part, we actually can define your specific tasks. So in this example, users define 2 different Hive tasks along with dependencies between each other. And then once this code is instantiated, it essentially creates a directed acyclic graph with a workflow where you have execution task, retention task, and they depend on each other. So while this is actually not a lot of code, it's actually doing a lot of functionality for users. Handles connecting to systems such as Hive, running on specific cadence. It also handles things such as retries, as well as data center semantics. So once we chose the system, essentially we decided to deprecate all the other workflow systems at Uber. So essentially all the workflows that are running on Uzi or the other ones we migrated into our system. And this makes sure that we actually didn't have to manage all these overlapping systems anymore after that. Also for users, once we kind of chose this, we were able to simplify life for the users. Essentially they didn't have to learn about all these different systems, and we can actually provide better documentation on our single system that we're managing. So now that we chose the system, we have to figure out how to deploy and scale the system. Essentially, we're getting a lot of workflows added, and we want to make sure that the system was scalable for the future. And we thought of a couple different ways to actually deploy the system in order to scale it for the future. So one option is to have a deployment or a cluster per team. So essentially, you'd be firing up a cluster of this workflow system for each team that is using that. So it's kind of split out and separate. But you might end up with actually 30, 40, or even 100 different clusters at the company. So they're all clusters that you have to actually manage. The other option is having a single multi-tenant system across the whole company. So in this example, the whole system would actually share all the workflows together, and you'd be managing it through a single system. So essentially, there are some trade-offs in this, and thinking through it, kind of thinking the options through. So one of them is who would be responsible for actually configuring the system and making sure it's running. So if we have 30 or 40 different clusters, the user might need to do some work and tell it kind of what kind of capacity they need, different options such as that. But if it's a single cluster, our team can easily manage that as well. Also, upgrades is another factor. Anytime you have 30 or 40 clusters, it's more difficult to keep that in the same version. Versus a single cluster, it's much easier to upgrade as well. On-call is another factor, so being on call for dozens of clusters is more difficult than a single cluster as well. Efficiency is actually a good one to think about as well. Anytime you're splitting things into separate clusters, you can't get as good of an efficiency. So some clusters might actually be underutilized, while others are overutilized. Having a single system can actually drive your efficiency to a level that you want and make sure that your efficiencies are at the peak level. And finally, scaling is the last thing to think about. It's actually easier to scale the system by just spawning different clusters versus a single multi-tenant system is actually harder to scale, so we need to make sure that's actually more scalable. So once we thought about all these different options, our team decided to go with a single multi-tenant deployment that's managed by our team. So essentially with this, our team manages the system, and it's transparent to the users. So the users don't have to know any details about the specifics of the system. Our team is able to provide office hours, deal with feature requests and bug fixes, and basically provide a better experience for the users. Once we chose this method, we definitely had some challenges, so I'll go through that in future slides. And also another thing to think about is that once we went with a single cluster, we needed to scale, make sure it's scalable to a higher number of workflows within that single system. So we've done a lot of re-architecture essentially to meet that goal, but before I cover that, I'll cover some basic system architecture so you're more familiar with the different parts of the system. So essentially this is the V0 architecture. This was actually based on the initial Airflow architecture. You can see this was a couple different components that essentially provide the system as a whole, including the scheduler, workers, and other components. And I'll cover those in detail in the next slides. So the first component is the Python workflows. Essentially, these are the DSL, Python DSL that I showed you previously. And essentially, users author these DSL workflows. Our team also provides a set of off-the-shelf tasks that users can use, including Hive, Spark, Presto. However, users can actually write their own custom tasks as well. So they can actually write custom code that connects to services at Uber or data systems as well. And at Uber, we actually run a monorepo with all the workflows. Currently, the monorepo is close to about 1 million lines of code for that monorepo. And we run through a series of unit tests that run each time a new workflow is checked in to make sure that it's running correctly. And then once it's landed, it gets deployed automatically to all the different components in the system. The next component is the scheduler. So this is essentially the heart of the system. This ensures that the workflows are kicked off in the correct cadence, that the dependencies are met between all the different tasks, and also handles more advanced options, such as retries, specific data center semantics, as well as backfills. So the schedule is kind of the part of the system that needs to be make sure that's running in order for the system to work correctly. The workers are essentially the place where the code executes. As I mentioned, it could be tasks that actually our team has written and supported by user, or actually custom code that users write as well, that they want to connect to different systems. As I mentioned, there's a wait maintenance UI, so there's some API endpoints, UI endpoints that we're serving, and we also have some APIs that can be used for workflow state or for triggering different workflows. So web servers are essentially a component that actually serve these endpoints, both for the UI and the APIs. And finally, the metadata database. This is the database that has the source of truth for the workflows, tasks, and their states. So you can see with this architecture, we have the scheduler, workers, and web servers all connected to the Python workflows and the database. So now I'll talk about isolation and multi-tenancy. So as I mentioned, when we essentially chose the system, we wanted to have a goal of having a very flexible DSL. And with this DSL, it's basically a Python-based DSL, and you can essentially write whatever you want with that. And actually, at Uber, we actually use that to its full extent. We have some pipelines, some single Python files that maybe generate thousands of workflows from that single Python file. So it's definitely very powerful. On the other hand, it's some danger involved with that. As it's Python code that users are writing, they can actually do anything they want with that. So this includes, writing for loops, talking to the database, calling out to services. So all these can actually be slow to load, or it can crash. And it can actually impact the system in terms of availability and performance. So whenever you're actually thinking about a multi-tenant system, this is kind of the ideal picture of a multi-tenant system. So essentially each tenant is isolated from any other tenant. So in this case, let's say if some user checked in some bad code, it actually doesn't impact any of the other users. So it's completely isolated from each other. However, what we found is more like this. Basically, cars can park anywhere they want and then block other cars in. So in our case, users would check in bad code, and it was actually impacting our system and other workflows within the system as well. And our goal was actually to have a self-service system, which means that our team doesn't actually manage the code that the users write. We don't have to review that. We just let them commit that code as well. We have to do some unit tests, but essentially, as I mentioned, we have almost 1 million lines of code on our workflows, monorepo, and we have almost 100 commits a day. So it's actually not scalable for our team to manually review users' code. So ideally, any user code that is bad should not impact any other parts of the system. And here's a diagram that illustrates this, of what essentially is loading user code and can be impacted by bad user code. So first, there are the workers, and as I mentioned, is actually execute the code, so it actually has to load the Python code for that. On the other hand, the scheduler is also loading the user code. So essentially, whenever any of these tasks are getting scheduled, the Python DSL that users write have to get loaded initially. So obviously, this can impact the system. If a user writes bad code that's slow to load, it can actually slow down the whole scheduling, or even stop the scheduling of the system as a whole. Also, the web servers also load the code as well. So essentially, whenever a user visualizes their workflows, the web servers essentially have to load that code to get the structure of that code. So if any bad code was checked in, essentially these web servers would be slow to respond to those endpoints. So the question is, how do we isolate user code from other parts of the system? So essentially what we came up with was, what if we actually can extract that metadata from the workflows? So you can see the Python code is on the right, but it has actually a certain structure to it. It has certain properties, a certain number of tasks with dependencies on each other. What if we can actually extract that structure into a serializable format that no longer has to be loaded by other parts of the system? So what we've done is introduce a serializer component. So essentially this component takes that Python code on the right and essentially will serialize it in a JSON-based format. So essentially it runs through all the different Python code in a monorepo and will convert it into a serialized format and store that in the database. So here's the architecture after we've introduced this change. So you can see user code essentially enters through the workflow serializer and is serialized into the metadata database. So in this respect, you can think of the workflow serializer as kind of a firewall for user code. So essentially once that user code is serialized, it goes into the database and no other components have to load that. And we can actually do things to basically harden that component and make sure it deals with failure in a better way. But now the scheduler no longer has to load that code, which means the scheduling can be much quicker and it's not impacted by bad user code. Same for the web servers. The web servers now can respond to these endpoints by just having to load the JSON formatted metadata, not have to actually load that user Python code. So once we introduced these changes, we definitely noticed our system was improved. So we actually no longer had to police all this user code, and our reliability and system availability was also improved, as well as our on-call as well. However, there's one other issue, is high availability and scalability. So essentially the question is, how do we deal with failure in a dynamic environment? So at Uber, we actually run all microservices on Mesos. This means that actually any of these containers, they actually run in Docker containers, but any of these containers can disappear at any time, similar to Amazon machines as well. This can be due to things such as deployments, hardware shortages, resource shortages, or any other reasons. But basically, good system design dictates that if any single component fails, your system should not go down as a whole. You should be really resilient to these types of failures. So yes, there should not be any single points of failure in your system. And this diagram kind of illustrates the single points of failure that we had in our system. So essentially, the scheduler was the first single point of failure. So this means that the scheduler actually, the container actually went down. Essentially, the scheduling would stop and no workflows are getting scheduled. So essentially, this would be an outage for our system. The second component is the workflow serializer. Also, if that went down, essentially no new workflows can get added to the system, or workflow changes would also not be impacted. So essentially, this is not an outage, but it's definitely not an ideal situation. The other issue we found is issue of scalability and scheduling latency. What we found is that the more of these workflows were getting added, the tiny scheduling was actually slowing down. And it's taking longer and longer for these tasks to get kicked off. And really, we're running a single Python scheduler, which we did fork some processes, but there's a kind of a limit of how many workflows a single node can schedule. So the question is, how can we use distributed systems concepts in order to solve these problems? What we decided to do is look at a distributed coordination service. These are services such as etcd or Zookeeper. And these services actually provide you distributed systems primitives that you can use to basically harden the system and make it more resilient to failures. And these systems actually distribute themselves. So a single node or two goes down, and it actually keeps working as long as there's a quorum between them. So now I'll cover what kind of things you can actually build with these types of systems. The first thing you can actually utilize is leader election. So essentially, anytime you have a single component that needs to provide a function, for example, in our case, the scheduler, you can actually use leader election so that you can actually have a pool of these schedulers to provide that function. When the system boots up, essentially it elects a single leader to serve that function. And now you have, if that scheduler goes down, essentially another leader will get re-elected automatically. So essentially there's no manual intervention. If the system fails, there's a live set of backups that are able to take over without any intervention. So this actually gives you much better high availability in this case. The other thing you can do is work partitioning. So as I mentioned, our schedulers will essentially schedule the workflows, but what if you can actually add multiple schedulers to the system, and you get a portion of the schedulers, a portion of the workflows assigned to each scheduler. So with the distributed coordination services, it gives you group membership, and you can actually use that to assign a portion of workflows for each scheduler. So this means that you can actually keep adding schedulers to the system, and then it would actually divide those workflows among the schedulers. If one scheduler goes down, essentially the system would detect that and reassign those workflows to the other online schedulers. So essentially this gives you better high availability and improves your scalability as well, as you can add more nodes in the system to scale out. So here's our architecture to summarize that with the single points of failure, the scheduler, and workflow serializer. So the first step is adding leader election for the workflow serializer. And this is kind of the first step we took to improve the system. So here with this diagram, you can see now that the distributed coordination service is on the right, and the workflow serializer now on the bottom left essentially is using leader election. So now we have actually a pool of these nodes that can provide that function. If one goes down, another one will automatically take over. The next step is to provide workflow partitioning for the scheduler. So you can see now we have the distributed coordination service and it's connected to a pool of schedulers. So essentially we have n schedulers in the system, and we can add new schedulers as we want. As a new scheduler is added, it automatically gets assigned a portion of the workflows. As schedulers crash, essentially those workflows will get reassigned to another online scheduler. You might also notice that we have a Java icon on the scheduler, so I'll talk about that next. So what we wanted to do with this, your architecture essentially is choose the best tool for the job. Once we actually serialize the Python code definitions into the metadata database, essentially we're no longer tied to using Python for the scheduler. And actually, within data, we use Java. It's used pretty commonly. So what we decided to do is essentially rewrite the scheduler using Java. And Java actually gave us better concurrency primitives as well, and basically gave us better efficiency within a single scheduler. Also, the libraries, like for example, some of these distributed coordination services are much better for Java as well. And in general, actually, it's encouraged within Uber to use either Java or Go for most services. So we wanted to follow along with that recommendation. So essentially what we ended up doing is taking our Python-based schedule and rewriting it completely in Java. And one last change we made essentially is introduce an executor component. So essentially, an executor is what submits these jobs to the worker system. So once a job is scheduled, it essentially submits it to either Redis or Celery, which is one commonly used executor. It can also be Mesos or Kubernetes. So what we decided to do is essentially extract that component into its own component. And here is our final E2 architecture. So essentially, you can see now we have the distributed coordination service. We've added the executor on the bottom right. It's also written in Java and uses leader election. And as before, we have the partition schedulers on the top using Java, and the workflow serializer with leader election. So you can see with these changes, we've added basically high availability and additional scalability as well. So once we've made these changes, we definitely noticed that our system availability was improved. So essentially, we no longer had to babysit any single server. So we can have some servers crash, and the system would actually keep running, even if it actually took Mesos a while to reschedule those servers. And also, our on-call was also improved, and as well as the scheduling latency was also improved due to the added scalability of adding new schedulers to the system. So this covers our re-architecture efforts, and I'll talk about how our system fits in at Uber. So essentially, this is a diagram of kind of the ecosystem around the workflow orchestration tool. In the center, that's the Piper platform, essentially. On the top are all the different services that we connect to. So essentially, that includes Apache Spark, Apache Hive, Presto. Our data warehouse is HP Vertica. Data Science Workbench is essentially our authoring tool that's based on Jupyter Notebooks. And Michelangelo is our machine learning platform. So we have ways to essentially connect to all these different systems within the workflow platform. As I mentioned, users can actually write their own custom code, so they can actually connect to other systems as well. That's not denoted in this diagram. Also in the middle section, you can see that teams have written actually libraries to enable users to use these tasks off the shelf. So for example, the Michelangelo team, which is the machine learning team at Uber, has added libraries for machine learning or deep learning, as well as feature creation. So users can now use these tasks within their workflows. Also, the ingestion team has added libraries for Marmoray, which is an open source tool for basically ingesting and dispersing data. So this allows users to also leverage these tools in their pipelines. Also, within the middle section, you can see that teams have actually written frameworks that allow users to more easily write their workflows. So essentially, instead of having to write workflows in Python, these frameworks that allow users to write more declarative workflows. So the first example is a framework called IETL that our team actually supports that lets users write workflows in YAML. And essentially, this is best practices ETLs, which use dual promote and stage steps, add automatic data validation, and allow you to do either incremental full loads as well. So users don't have to know about all the different details for that. Other teams at Uber have also leveraged these types of frameworks, such as the AdTech team or the Uber Eats ETA team. And finally, the system of Piper at Uber is actually being used to schedule for other teams as well. So there's maybe other domain-specific use cases where there's UIs that users can use, and under the covers, it uses our system to schedule those workflows. So as an example of that, Michelangelo, the machine learning team, uses our system to schedule workflows for feature creation, as well as machine learning and deep learning training. There's also other systems that help the machine learning data preparation, essentially letting users do drag and drop workflow creation. Our team actually also supports another tool for creating workflows that build dashboarding related ETLs. The ingestion team also has built something where essentially users can use a user interface to ingest data from Kafka into Hive, and which uses our system to schedule these workflows as well. And finally, our team's working on a new product which lets users create drag and drop based workflows across streaming and batch. And it's actually using an open source tool called Streamline, which is a tool by Workworks. So here are some stats. Essentially, we have around 20,000 workflows that we're running. This architecture that I mentioned has been in production for about a year and a half. We have about 2,500 users plus that are using the system. And our workflow monorepo is almost 1 million lines of code. So now I'll go through some takeaways. So first is the importance of user-friendliness and expressiveness. And this was apparent when we chose a system, make sure that the system was approachable to many types of users and has a nice maintenance UI and management capabilities. Next is the importance of converging to a unified platform. So this essentially helped our team not to have to manage all these overlapping systems and focus on a single product, and also ensuring that users are also easier for them to use this as well. Next is the importance of isolating user code and components. So essentially this ensures that we can actually have a truly self-service platform that's multi-tenant and is not impacted by bad user code. And finally, the importance of using distributed systems concepts such as leader election and work partitioning to make your system more highly available and scalable. These are some acknowledgments of some teammates that have worked on this system, as well as some people that have helped with the talk, so thank you. And that is the talk. There's also a blog article that covers some of these content as well, and here's contact information for me.
I'm the person who knows how to use it for pretty pictures.
So with Piper now, is there any need for Apache Airflow?
Pardon?
Using Piper, now do you have any need for Apache Airflow?
I mean, that actually serves that function for Apache Airflow, but as far as, yeah, that's essentially that's Yeah, but I mean, we're actually talking with some of the Apache Airflow system to try to make some of these changes into the like mainline to at least help them out with putting these same changes in.
You just mentioned that the Python-based workflow definition will be serialized to JSON by the workflow serializer, right? But in that case, the serialization part will also take the user code, right? So how do you prevent the user codes from misbehaving in your workflow serializer?
Yeah, that's definitely a good question. So the one important factor is that the serialization doesn't have as tight of an SLA than the scheduling. The scheduling, for example, we want the scheduling to be very fast and not be impacted by user code. And the same for UI, the UI as well, right? You don't want the UI endpoints to have load that user code. As far as the serializer, that's something that maybe the SLA is not as tight, but we can actually do things such as timeouts or things like that to make sure that to harden that system as well. But the SLA is definitely not as tight on the serialization as it is on the scheduling and the UI.
I also had a question on that part.
Yeah.
So you serialize the source stored on the database.
Yeah.
But then you have essentially have to serialize in order to for scheduler, UI, and all the other pieces you use it. In that case, the backcode will go back again. So is that
Serialized meaning, so there's two different things, right? There's the Python structure. So right now, like for example, Airflow will actually load the Python code for the scheduler and the UI. But we essentially serialize it to JSON. So from JSON, we just load the JSON. The serialization for JSON is very quick. Right? Yeah.
Any other questions?
Thanks for talking. So my question was regarding one of them is the measuring the schedule miss or the SR miss of scheduling.
Yes.
I'm wondering what kind of metrics are tracking? For example, if the task is delayed not because the scheduling delay, but because of the dependency delay, how would you account this into the delay of that scheduling miss?
Yeah. So we have we measure mostly when the task for example gets queued and how long it takes for the queue task to get executed. So we have metrics around that. We also have metrics for some canary-based pipelines, so we know our pipelines that don't have any dependencies of how long to run. For the dependencies that would throw our metrics off, so that's why we don't actually measure that part of it.
So another question is that I know there is another system called Cadency also in
Yes.
Uber. What would be the difference here?
So Cadence is more for business workflows. So a lot of teams use Cadence, for example, if they have, let's say, like a single every trip where each order needs to actually perform some function, like send an email or do another type of function. Typically, at Uber, those Cadence is used for that. Within Uber, Piper is used more for data-related orchestration. So we provide an easy way to connect to all the different systems, such as Hive, Spark, and all the security around that. So if people use Cadence, essentially, they would have to re-implement a lot of that as well.
I have a question for the SR minister. When a high priority job is supposed to start at a certain time, if it doesn't start, how do you handle that in Piper?
If a high priority job,
Supposed to start at say, for example, 7:30 sharp, it needs to start, but the scheduler for some reason there's a delay, it doesn't start until let's say 7:45. So will Piper generate alert to the end user even before the job completes?
yeah, we have metrics that we emit when the task starts. We don't have prioritization as well, but that's something maybe like a future thing that we could add into the system. But as far as prioritization between different tasks, that's not something that's part of the current system.
Okay, cool, thank you.
Last question. No more? Thank you, Alex. Okay, we got one more talk from Uber. So this is called a Foodie. So it's recently got introduced as a Partitioning incubator